Hi. Okay, so this is my video number 14. Yeah, number 14. I'll talk on the solution of the non-homogeneous Volterra integral equation by successive approximation, particularly Neumann series. Yeah. Let me write those things. Solution of non-homogeneous Volterra integral equation. Volterra integral equation by successive approximation. Or also known as iterative method. Yeah, iterative method, and particularly we discuss on the Neumann series. Okay, so first I will describe how the successive approximation method works that leads to the Neumann series, to the solution of the form Neumann series, and then follow up with a theorem that I'm going to prove that theorem. Yeah. Okay. So first we consider the nonlinear non-homogeneous Volterra integral equation. So we have non-homogeneous Volterra integral equation. I just put it in short form like that. Yeah. Non-homogeneous Volterra integral equation. In the general form, we have ux is fx plus lambda a to x k xt ut dt. Yeah, homogeneous because this function is non-zero, and then Volterra because we have some constant to variable limits. And then we take u0 as a first approximation as fx. Yeah. If it is given, then we use the given one. If not, then we can use u0 as a fx, or we call it as a zero approximation. Yeah, we call it as a zero approximation. Approximation to our equation here. Okay, so and then the n term, this is the first term, this is the zero approximation, then the next, the n approximation and the un minus approximation, then the un and un minus 1 approximation, just like that. We have un is given as unx as fx plus lambda integrate a to x kxt un minus 1 t dt. Okay, this is the relationship between un and un minus 1. And then from the iterative kernel, iterated kernel, so we have k1 xt is k xt. We have I've written this many times. I wrote each time in lecture so that we can refer those things. So and kn xt, this is integrate t to x for the case of Volterra integral equation. Yeah? K xz k n minus 1 zt dt. I think this should be a, yeah. Okay, then and then from u here, let's call this let's call this is number 1, let's call this number 2, let's call this equation number 3. Then from 1 we can find what u1, we can find what u2, and then we can substitute u0 with fx and k1 with kxt, and so on and so forth. So that's the process. Okay, so let me write those. So let from 1, okay, we take n equal to 1 and use u0 equal to fx, our first approximation here. So we use u0 fx. Yeah, so what we got, that we have u1 x, this is fx plus lambda integrate a to x, we have k xt and u0 t. Yeah, u0 t is ft. So here is u0 t dt. Okay, so I can write this as a fx plus lambda integrate a to x kxt, u0 t is ft dt. So when n equal to 2, yeah, when n equal to 2, then from 1 we have, yeah, when n equal to 2, then from 1 we have u2x is fx plus lambda a to x. Just follow that, yeah, just with n equal to 2. So we have kxt, this is u1 t dt. Then I can write this, if I change t with something else, z for example, then I can write this is just equal to fx plus lambda a to x kxt z now, z u1 z dz. Yeah, we change t equal to z in that case. So this is our u2. Now we can substitute this u1 from here. This is our u1. Yeah. Let's say this is 4, but this is u1x. This, what we need is u1z. So let me write those things. So we're going to have, if we substitute those, we're going to have u2x. It's not really clear. Okay, so u2x is equal to, so we have fx plus lambda integrate a to x k xz u xz. So u1 with z, so we have those things, fz plus lambda integrate a to x k x, we change with u1 z, so x with z. So this is z, should be z, this is z t ft dt, right? Yeah, ft dt. So we have those lambda 0 to z, yeah, ft dt, ft dt and dz. Alright. So we rearrange that. So what we have, this is fx plus lambda a to x kx z fz dz plus we have lambda squared integrate that one is z. I can put z equal to a to x kxz, and then we have z terms integrate. This is for t from a to z. We have k zt ft dt dz. Okay, now we're going to change the order of integration. So instead of we have integrate respect to t first then dz, now we want to change to dz first and then dt. So in order to do that, but we can look at the limit of integration. Yeah, look at the limit of integration. What we have is that z t from a to z, and then z from a to x. Yeah, so z from a to x. Yeah. So if you look at that region of integration, so what we have, this is our t, this is z. Yeah, integration with respect to t and z, so t that's z, and then we have z equal to t there, so I can, let's say, write this z equal to t. So let's say this line is z equal to t. Yeah, this is z equal to t, and then we have t from a to t equal to z, so which means t equal to a somewhere here. So that's, we integrate up to t equal to z, and t equal to z when z equal to x. When z equal to x, so which means up to t is from a to x. So which means x, let's say somewhere here, that x. Okay, this is z. So I can have those, and this I can have here. Okay. So this is z equal to a. Here is, this is z. This is z equal to x. Alright, that's z equal to x. That line here. So then, with that we can see that the region of integration. So this is the region of integration. Alright. So instead of we do on t first, then we want to do on z first. I think you can do this thing, and from there you can see that z from a here to that line, which is z equal to x. So after the change of order of integration, we have z from a to x. Okay, and then t, we have t from a to x. So t from a to t to x. So therefore our integration here, just look at those. Alright, I just take that part here, dot pass. So let me write those things. Z equal to a to x k x z integrate t z a to z k z t f t dt dz. Okay, so I can write this as a integrate. Now instead of z, now I want to integrate t from a, t from a to x, t from a to x, and we have ft, and then the rest is integrate z from a to x, z from a to x. Okay, so k xz and kzt, that we have dz dt. So if you recognize this, if you consider this k as k1, yeah, from the iterated integral, first term of the iterated integral, we have k1 equal to k, so I can consider this as a k xt, k1 xt, and then the whole terms here, this is actually k2 xt. Correct? So therefore I can write those integral here. Let's call number 5. So therefore I can write the integral number 5 as, and using that part that this is k2, and here this is k, basically, yeah, and for k2 here, for k, the second term here, this is I can write as a k1. All right, so we have k1, we have k2, and so on and so forth. So what we have now is u2 x is equal to we have fx plus lambda integrate a to x. Here is k xz fz dz, and I can write this because this is variable of integration, so I can put t here, I can put t here, I can put t there. Okay, plus that one as a lambda squared integrate z from, we can change to t. Okay, I use this first, a to x. Here I can have k, no, we have changed those things. Let's come to here. So lambda squared t equal to a, t equal to a to x. So we have, this is k2 xt ft dt. Okay, and this one, as I said earlier, I can write this as a k1 because from the iterated kernel. Now with that, I can write this in terms of using sum notation. So this is equal to fx plus sum m equal to 1 to 2, 1 and 2. We have lambda m, then we integrate from t from a to x, and we have k, here we have m xt ft dt. Alright, and then we can proceed further this up to, we can obtain up to n terms. If you proceed further, you can obtain up to n terms. So that's the n approximation. We have u and x. This is fx plus summation dot m equal to 1 to n lambda m you integrate a to x km xt ft dt. So to obtain the solution to our system, to our equation, I mean the non-homogeneous Volterra integral equation, so we need to take a limit n goes to infinity, then we obtain u, provided that those limits converge. Okay, so we take, so therefore for the solution, we take a limit n goes to infinity. So what will happen here, we get u of x is actually limit n goes to infinity. We have un x. This is equal to, we have fx plus those summation m from 1 to n, now it comes to infinity. So lambda m integrate a to x km xt ft dt. So this is, we call it as a Neumann series. Yeah, this solution we call it as a Neumann series. Okay, so this this we call it as a Neumann series. Neumann series solution. Now, to obtain the resolvent kernel, we need to change the order of integration here. Integration and the summation. So if we do that, so what we have, this is ux, this is just equal to, we have fx plus I can write this as we can take out 1 lambda m because we want to write in terms of resolvent kernel. So I can take out 1 lambda and then we integrate from a to x, then we sum up m from 1 to infinity. So that one we have taken out 1, so what left is lambda m minus 1. Okay. And then we have km xt, then we have ft dt, yeah, km ft, yeah, ft dt. So we have this term here, that mft, yeah, and this part here is the resolvent kernel. So we can write this as a resolvent kernel x t lambda as a summation of m 1 to infinity. We have lambda m minus 1 km x t, and this series converge, yeah, absolutely and uniformly when k is continuous in R, in the region. So this is the solution of the non-homogeneous Volterra integral equation in terms of Neumann series. In terms of Neumann series, we use the iterated method. Okay, so now let me prove one theorem. So what you need is, in order to solve this equation, you need just need to follow the step that I have explained just now. Yeah. So let me prove one theorem. So this theorem says that if or let Rx T lambda be the resolvent kernel, okay, of the Volterra integral equation, the Volterra kernel of the Volterra integral equation, ux equal to fx plus lambda integrate a to x kxt ut dt. Then those resolvent xt lambda satisfies this integral equation. So r xt lambda equal to k xt plus lambda t to x k xz r zt lambda dz. So we're going to prove this. It's not really difficult to prove that, just you need to use the iterated kernel, yeah, and the properties of the resolvent kernel as well. Okay, now, so to prove this, the resolvent kernel is given as we know that the resolvent kernel is given as xt lambda. This is a summation of lambda m minus 1 km xt, where m from 1 to infinity. And the iterated kernel, as we know, the iterated kernel given k1 xt is k xt and k m xt. This is integrate t to x k xz k m minus 1 zt dz. Now, from the given resolvent kernel here, yeah, definition of the resolvent kernel. So I can write this, let me write this as a 1. So from 1, we can write r xt lambda as, you can take out 1 k, so we have k1 xt plus, we have some m from 2 to infinity, you still have lambda m minus 1 km xt. Okay, so what we did, we just take out 1 k1. K1 is equal to k. So remember that the purpose is we want to write this. Alright, this is the end result that we want. So we already have the first term that we have k using that relation. Okay, so using those two relations, the iterated kernel relation, that one and that one. Okay, so what we have now are, I can write this as equal to, this is kxt, k1 is equal to kxt, plus we have some m 2 to infinity, so we have lambda m minus 1, lambda m minus 1, and km is given as this, so we have integrate t to x kxz km minus 1 zt dz. Okay, so I want it here becomes 1, not begin from 2 but begin from 1, so we minus 1. So let's say I change that, let n equal to m minus 1, then we have our r is given as r xt lambda, this is kxt plus, so n from 1 to infinity, so we have lambda n integrate t to x. Here we have kxz kn zt dz. Alright, so we have those are lambda m. Of course, here this is m. We want to make it where is it here? R, our R is defined as this Rm. So I can change the order of integration, or in fact I can write m instead of m. I can put n, yeah, instead of n I can put m, instead of m I can put n, and so on. That's just a counter. Alright, so then I can write this as a k xt plus, we have lambda, you take out one lambda, sum n from 1 to infinity, so we have lambda n minus 1, integrate t to x k xz kn zt dz. Then we change order of integration and the summation. So what we have, I can write this as a k xt plus lambda, then integration we put it out, t to x, we have k xz, and we have summation lambda n minus 1, this is from n to infinity, and we have k n zt dz. Yeah, zt dz. Okay, and we recognize that this part here, this is rz t lambda. So therefore we can write this, this is equal to k xt plus lambda tx, we have k xz r xt zt lambda dz. So this is what we want to prove in the theorem. Okay, so that's the proof of the theorem that the resolvent kernel of the volterra integral equation of the non-homogeneous volterra integral equation can be written as that equation. Yeah, rxt lambda kxt plus integrate t to x k xz rt lambda dz. Okay, so what I've done in this video, basically I have explained to you how to use or the method of successive approximation or iterative method leads to the Neumann series, and those Neumann series is uniformly convergence. So with that, I stop here for this video, and for the next video I think I have a few examples to discuss with. Right, so for this video I'll stop here. Thank you. Bye.